uh, present the solution. So the question is there on your screen. It is a question to find the equivalent resistance between point A and B, and please try it out. And if you have solved it, so if you have solved this question, you can put the answer in the chat box. Okay, let's look at the solution for this. So you need to find the equivalent resistance across this point A and B. So we have two complicated networks in this. Now, are you guys familiar with the Wheatstone bridge? Can someone confirm? Sorry. Okay. So here in the first network, you can see that the resistance 418 and 29, these are proportional. So the voltages at these points will be equal, and hence the 5 kilo ohm resistance can be removed. Uh, and in the other cases, that this particular wire is effectively short because you have 0 kilo ohm resistor over it. So this is what you get as the final equivalent network. So you have a 2 kilo ohm resistor, then you have an 18 and 9 kilo ohm resistor, and 4 and 2 kilo ohm resistor in the parallel. Then you have a 5 and 3 kilo ohm resistors in series, sorry, parallel, and then two 2 kilo ohm resistors in the parallel. So if you try to calculate the RAB, that will be 2 plus the resistance of this network plus the resistance of this network plus the resistance of this network. That comes out to be 9.78. So any doubt in this? Okay, so let's move forward. So the next question is on screen. Please try it out. I will give you some time and then solve this. If you have solved it, you can put the answer in the chat box. So these are the options out of this. Which one is correct? You can put it in chat box. Okay, so let's see how to solve this question. So you have a series and parallel combination of resistors. Now let's look at the option C. So what you have is this is what you will get if you substitute R1 as R and R2 as 2R. So uh, in the first two resistors over here, these are in series and they become 2R, and then 2R and 2R in parallel. So 2R into 2R divided by 4R. So this again becomes R. So this becomes R. Now again R and R 2R. Then again it will become R, and this will keep on repeating till the last point. Here you will get R. So the total equivalent resistance between A and B will be R plus R is equal to 2R. Any doubt in this? Okay, if there is no doubt, we can move forward. Now, so I have worked it backwards. So in practice, what you should have done is, you should have calculated the complete resistance in terms of R1 and R2, and then you could have plugged in the values and checked. So it will be 2R1 plus, and other thing is that 2R1 into R2 upon 2R1 plus R2. Similarly, this will keep on going. So the thing is that if you have this kind of questions, there is some repeatable pattern that you can observe. Okay. So like these kind of things you can even try to remember that yeah, if you have this kind of ladder, then no matter how much the length of this ladder, ultimately you will get uh, the value r over here. So yeah, if you encounter some new thing, just try to recognize some pattern, and then you can proceed. So next question. uh, so we have two current sources pumping in the current into this network, and these two nodes are grounded. You need to find the value of IA, IB, IC, and the voltage developed across 3 kilo ohm. So, uh, first of all, find the value of IA, IB, and IC. I will give you some time, and if you are done, put the answers in the chat box. So, yeah, please try it out. Okay, so let's proceed with the solution. So, uh, you guys might have read KCL and KVL by now. So, that's what you are going to apply in this question. So, we have current IB and IC flowing like this. So, at this node, if we see, we have current 5 milliampere coming into the node and our current IA leaving the node. So the current that will be flowing in the 4 kilo ohm branch will be 5 minus IA. Similarly, current that will be flowing in 3 kilo ohm branch will be 2 plus IA. And these two voltages are ground, that are 0 volts. So, and since this is a short wire, so voltage developed across 4 kilo ohm branch and voltage developed across 3 kilo ohm branch must be equal. Why? Because this is 0 volt and this is a short node. Okay. So, if you equate the voltage developed across 4 kilo ohm and 3 kilo ohm, that will be 4 into 5 minus IA plus is equal to 3 into 2 plus IA. So, from there you get a value of IA as 2 milliamperes. Now, consider this complete network. So, in this complete network, whatever current goes inside must be uh, equal to 0. So 5 plus 2 plus IA plus IC is equal to 0. Why? This is again Kirchhoff's current law. So Kirchhoff's current law can be applied both at a node as well as a complete network. If the network doesn't stores any charge, then like whatever current is going must be equal to the current that is leaving. Okay, in this case, either value of IB or IC will be negative. So, uh, yeah, before that, since like these two voltages are zero, so the voltage developed across 2 kilo ohm resistor will be zero. So that you can equate to zero. From there, you get the value of IB as minus 3 milliamps. And then since IB plus IC is equal to minus of 7 milliamps, from there you get IC is equal to minus of 4 milliamps. And to calculate the voltage developed across 3 kilo ohm branch, so you have the current flowing as 2 plus IA. IA was 2 milliamp. So uh, 2 plus 2 into 3. So this is in milliamps and this is in kilo ohms. So milli and kilo cancel and we get 12 volts. Any doubt in this? Okay, so if there is no doubt, sorry, Ayush, you were saying something? Okay, so let's move to the next question. Okay, now again, you have to find the equivalent resistance looking in by this voltage source V in. Please try it out. I will give you some time and then we will solve the question. And if you are done, you can paste the answers in the chat box. Chari, can you please turn that off? Class is going on. Thank you. Sorry. Okay, so let's proceed with the solution. So now this is a dependent source. Can anyone tell what kind of dependent source is this? Out of current controlled current source, current controlled voltage source, voltage controlled current source, or voltage controlled voltage source. Which one is this? Can anyone please tell? Okay, so the controlling, yeah, uh, Ayush, yeah, correct. So the controlling parameter is a voltage, that is V in, and the output parameter is a current. So it is a voltage controlled current source. Now, uh, at this node, the current that is flowing inside the this branch is B times V in, and current that is flowing through 5 kilo ohm resistor is I in. So by KCL, you get I in minus BV in current flowing in 3 kilo ohm branch. Now, if you apply the KVL in this particular loop, you will get V in minus 5I in minus 3I in times BV in. Now, in the question, we have been given B as zero point 0.1 milliamp by volts. So, if you solve this, you get your answer as 8.8 by 1.3 kilohms. So, it's somewhere around 6.18 kilohms kind of thing. So, yeah. Now, this is a question that is uh, similar to the question that we saw for resistor. So, for what value of capacitance of C1 and C2, we will get the equivalent capacitance as C by 2. Please try it out. Okay, let's see the solution for this. So now, see, again, you need to see the repeating pattern. So now, irrespective of the length of this, the seventh question. Okay, I will explain it after this particular question. Uh, so yeah, the length of this, irrespective of the length of the network, the capacitance at this point must remain same. So, what is the capacitance of one section? That is C1 by 2 plus C2. So, uh, and this and this must be uh, equal to again C1. Okay, so C1 by 2 plus C2 equal to C1. And if you solve this, you get C2 equal to C1 by 2. Okay, now if you have, like, no matter how many sections are there, the total capacitance looking in will be C1. Okay, so in that case, the total capacitance from at node AB will be C1 by 2, because when capacitors are in series, they are opposite of how the resistors act in the series. So if there are capacitors of value C in C, C and series, then you will get the equivalent capacitance as C by 2. So uh, we have C1 by 2 is equal to C by 2, hence C1 equal to C, and C2 equal to C by 2. Any doubt in this? Okay. So in these kind of networks, irrespective of the length of this particular network, the total capacitance that you need at this node must be uh, same. Okay. So uh, how in what particular case this thing will happen is, so let's consider the equivalent capacitance of one particular section. So what does it comes as? There are two C1 in series, so its capacitance will be C1 by 2, and then there is one capacitor C2 in parallel to it, so total capacitance will be C1 by 2 plus C2. Now, in order to have same capacitance at the end of this section also, the capacitance looking into here must be equal to C1. So we equate C1 by 2 plus C2 equal to C1. And from there we get this relation, C1 by 2 is equal to C2. And yeah, if you keep on going on like this, the overall capacitance into this ladder will be C1. So the equivalent capacitance between A and B are 2 C1 in series, that is equal to C1 by 2, and you want this capacitance to be equal to C by 2, so C1 equal to C, and hence C2 equal to C by 2. Okay. Now question number 7 again. So what we need to do is, in any kind of question where we need to find the current and voltages, we must solely rely on KCL and KVL. Okay. So first of all, we need to see that we have a loop over here. Okay, let's call this L1. Now, to apply KVL in this loop, what equation we will write? We will write the following equation: V in minus 5 times I in. I am dropping the kilo and milli for simplicity. So V in minus 5 times I minus V 3 kilo ohm. So we need to find first V 3 kilo ohm in order to make this equation complete. Okay, and now how we will find the voltage across 3 kilo ohm? We need the current that is flowing into 3 kilo ohm resistor. So to find the current that is flowing into a 3 kilo ohm resistor, we will apply KCL at this node. So the current coming in is I in, the current leaving out is B times V in. So the current flowing in 3 kilo ohm resistor will be I in minus B times V in. So now we can uh, apply the KVL in this loop. So V in minus 5 times I in, that is the voltage developed across 5 kilo ohm resistors, minus 3 into I in minus B times V in, that is the voltage developed across 3 kilo ohm resistor. This will be equal to 0, and from there we can find the value of V in by I in. Any doubt in this? I hope you understand. So Shruti, are you able to understand it now? Sorry, where? No, B times V in is the current. It's not the. Okay, yeah. So this might be confusing. This B is not a resistance. You must check the units of this. It's milliampere by volt. It's actually conductance. It's not resistance. Okay. Now in this question, you need to find the value of I naught as well as Ix. Please try it out. Okay, so let's see the solution for this. So first of all, let's find Ix. Now to find Ix, we need to find the equivalent resistance that this 7 volts will see. So for that, uh, how we will proceed? So first of all, these 2 kilo ohm resistors in parallel, that will be 1 kilo ohm. Then 1 kilo ohm and 2 kilo ohm series, that will be 3 kilo ohms. Then 1 kilo ohm and 3 kilo ohms in series, so that will be 3 by 4 kilo ohms. And then uh, 3 by 4 kilo ohms and 2 kilo ohms in series, parallel, that will be 6 by 11 kilo ohms. And then in series with 2 kilo ohms, so equivalent resistance comes out to be 28 by 11 kilo ohms. And if you divide it by the voltage, you will get current Ix as 2.75. Now uh, you have this looking in resistance as 6 by 11 kilo ohms that you calculated during the process. Then what you will do is you will apply resistor divider. You are familiar with a resistor divider, I suppose. So if you have R1 and R2 in series with a voltage source V, so let's say the voltage across V2 is R2 by R2 plus, sorry, R2 by R2 plus R1 times V. So similar concept you will apply. This is R1 and this complete thing is R2. So from here you will get the voltage across this particular network, and whatever voltage is developed across this network will be divided by the total resistance in this branch. That will give you that the current I naught that is flowing in this branch. So total resistance is 3 kilo ohms, and from there you can find the value of I naught. First of all, to find the value of voltage, that comes out to be 1.5 volts, and the value of I naught comes out to be uh, zero point 0.5 milliamps. Any doubt in this? So how do we get it is, so let's say we have R1, R2. Let's generalize it. Let's say we have N resistance in series, and we have a voltage connected to this network. Now the total current that will be flowing through this complete network will be V divided by R1 plus R2 till Rn. Now this current, this is the same current that will flow through all of the resistors. So if you want to find the voltage across one of the resistor, will be this current multiplied by the value of that resistor, let's say Rk. So this will give you the voltage across kth resistor, and this can be done for specific case of two resistors where only you have R1 R2. So in that case, V2 will come out to be V into R2 upon R1 plus R2. Now similar concept can be applied for current divider also. I will encourage you guys to derive it. However, how you will have it is, if you have R1 till Rn, you have these many resistors in parallel, and current source flowing through it, and then how you need to find the value of kth current. So you can also try to find the expression of this. So please try it out. You can try it out at the end of the session. Let's proceed for now. Now, this is the next question. So please try it out. Okay, let's see the solution. So again, you need to find current I1. So for that, let's say you apply KVL in this loop L1. Okay, so what will be that? 1 volt minus 1 into I1 minus the voltage developed across this, sorry, the voltage developed across this 10 coulomb resistors. Okay, so now to find the voltage developed across this 10 kilo ohm resistor, you need to see KCL at this particular node. So you have I1 coming from here and 4 I1 coming from here. So total current will be 5 times I1. So uh, the V10 will be equal to 5 I1 multiplied by 10. Okay. So from here, you will get this I1 plus 50 I1 is equal to 1 volt. And I1 comes out to be 1 by 51 milliamps. That translates to 19.6 microamps. Any doubt in this? Okay, let's move forward then. Okay, so in this question, you need to find the open circuit voltage VAB and short circuit current ISC. Okay, let's see the solution. So first of all, VAB. So we have 3 kilo ohms. Okay, let's. So what we have over here is now this 2 kilo ohm resistor is uh, open-ended at one side. So no current will flow through it. I will be zero across it. So the voltage developed across it will be zero. Now whatever voltage that has to develop across VAB will be the voltage that develops in this branch. Uh, Now this 1 milliamp current has no other path other than this one, because this side it's open circuit. Okay, so this 1 milliamp will flow through this 3 kilo ohm resistor, and hence the voltage developed across this will be 3 volts. And please note, I am following the passive sign convention. So if the for passive devices, if the current is entering into this node, then this node will be considered positive. Okay, so we have 3 volts plus 5 volts. So it is the voltage in same polarity, hence 3 volt plus 5 volt. So VAB comes out to be 8 volts. Now for short circuit current. So uh, in this case, you need to apply again the KCL KVL equations. So what is the voltage developed across this node? Let's call this as some V naught. So the current that will be flowing in this direction will be V naught divided by 2 kilo ohm. Okay, so that will be the same current that is coming in this direction. So V naught by 2 kilo ohm, and the total current that will be flowing into 3 kilo ohm will be V naught by 2 kilo ohm plus 1 milliamp. So from here, the voltage developed across this will be V naught by 2 kilo ohm plus 1 milliamp into 3 kilo ohms. So from here, the V naught can be written as the voltage developed across 3 kilo ohm plus the 5 volt. So 3. Now I will take this kilo ohm inside. So kilo ohm, kilo and milli will cancel, and kilo will cancel in numerator and denominator. So V naught by 2 plus 1. So from here you get uh, V naught as minus 1 by just a minute, sorry. So V naught is equal to 1.5 V naught plus 3. That means V naught is equal to minus 6 volts. Okay, so the current ISC is nothing but V naught by 2 kilo ohms. So that comes out to be minus 6 by 2 kilo ohms. That is equal to minus 3 milliamps. Any doubt in this? Yeah. So this is called passive sign convention. So for all the passive devices, what you do is, since the passive devices always dissipates power, so what we consider is that the positive power is the dissipated power, and the negative power is the supplied power. So if the voltage across this is V and the current going in is I, so power will be is equal to V times I. Now consider a voltage source. So let's say it gives V volts, and the current that is leaving through it is now current is leaving through positive terminal. This is an active source. Okay. So in this case, power will be equal to minus of V times I. So this is the power delivered. So this is called passive sign convention. You can learn more about it in Hyatt and Kemerly book. I think you must be aware of that. So yeah, in the first or second chapter, this is explained. Okay, so this was it from my side. So any other doubts? Yeah, yeah, I can hear you. Yeah, IIT Madras. Okay, yeah, okay. So uh, inductors basic equation is a relation between flux and current. I hope you are familiar with this. So phi is equal to Li is how the conductance is calculated. Now let's ignore the coupling of inductance for now, that you will learn later in the course. So let's say we have sorry, two inductors connected in parallel. Okay. Now, in this case, please note that the flux is behaves in the same way as the voltage does. Basically, flux. So you might be familiar with the Faraday's equation, like voltage is equal to minus d phi by dt. Now, as the voltage across parallel combination is same for two devices, same is the case with the flux. Okay, so let's say this is L1 and this is L2, and the flux developed across it is let's say phi. So uh, the current flowing through L1 will be I1, and I1 can be written as phi by L1. Similarly, I2 can be written as phi by L2. Okay. So the total current flowing through this network is I1 plus I2. And from there you get I1 plus I2 is equal to phi times 1 by L1 plus 1 by L2. Okay. And this is equal to, let's say, some I equivalent is equal to phi divided by L equivalent. So L equivalent comes out to be 1 by L1 plus 1 by L2. Now in the similar case, as the voltages are added in series, so flux are also added in series. So with the same logic, for series, the LS, so let's call it L equivalent parallel, and for L equivalent series, it comes out to be L1 plus L2. So using these two series combination equations, you can find the equivalent inductance of complex networks also. Yeah. So any other doubts? Okay, if there is no doubt, we can end the call. And Yeah, yeah, you are audible. Yeah, yeah. You will be shared the YouTube links for those sessions on the course webpage itself. So, any other doubts? Okay, then. So, this was it from my side. Thank you for attending.